Okay, we are starting. Welcome to the second week of this class. Yeah, great. All right, so a little reminder where we stand. Okay, so first of all, we have this equation for the energy that we obtain. D equals TdS minus PdV plus mu dN. All right, we are going to use it extensively during this week, I think. Okay, what is mu? Mu is chemical potential. Chemical potential. Potential. Okay, so and it basically describes how energy is changing with the number of moles, the molar composition of the system, right? The number of particles. How addition or subtraction of the number of particles basically changes the energy. Okay, so this is the chemical potential. What else we have defined? We have defined heat capacities. Am I wrong? Probably not. Okay, so we'll define it now. So by the way, again, the rule, if you're having trouble asking questions in English, you can try and ask in Hebrew and I will translate them, or at least try. Okay, so heat capacity. Heat capacity. What is heat capacity? It describes how the amount of heat of the system in the system changes with the temperature. So it's dq by dt. We can do the following trick. We can say that this is T dq divided by T by dt. Okay? And dq divided by T, we can simply say that this is ds. So we have T ds by dt. Okay? Right? So we have several, but this depends, this derivative over here depends on what kind of quantities we are keeping constant. So for example, we will have heat capacity with a constant volume, which is simply T ds by dt when the volume is constant, or we can have heat capacity when the pressure is constant. It's T, how the entropy is changing with the temperature. Okay? So heat is related to entropy. We will discuss it maybe again later. And we see that the heat capacity is a quantity that describes how much heat in the system changes with the temperature, and it's related to the entropy of the system. The problem with the entropy and the problem with heat is how do we measure it? Okay. All right. Additional thing that we have done are the Legendre transforms. What are the Legendre transforms good for? So I remind you. Consider the following situation. Okay. Usually, whatever we have done so far, we treated either energy or entropy, but usually energy. So the energy was a function. It's a function of state. Describes the equilibrium state of the system. It was a function of S, right, of the volume and of the molar number. Okay, we can go backwards to this equation over here and we see what are the variables that E depends on. So it's S, V, and N. Right. Now let's think what happens if my experimentalist friend cannot control entropy. Nobody really can control entropy. He can control temperature. Okay? So I want to actually do something, compute something using different variables. So a basic transformation of variables from SVN to some, for example, what is usually used is temperature, volume, and the molar number, okay, is achieved by performing a Legendre transform. Okay. By Legendre transform, what we mean is we subtract from the function itself, right? The multiplication of the derivative of the function multiplied by the variables. Okay, so I remind you again here, if f is a function of n, the Legendre transform of, let's have it, xr and xr plus 1 and I want to transform only those variables to the derivatives of f with respect to these variables, right? So ui are df to dxi. All the other xj constant, okay? Keeping all the other variables constant. Okay? So this is achieved by performing the following transformation, which is called Legendre transformation. G is a function of f minus a sum from I r plus 1 till n of ui xi. Okay? G will be a function of x1 till xr u r plus 1 till un. Okay? This is the Legendre transformation, and we have written on the board three different functions, or three? Yes, three. I think three different transformations. Any questions? No? Great. So what are the transformations? If we have initially S, V, and N, okay, so we can go from here to T, V, and N. We can go to S, P, and N, or we can go to T, P, and N. For example, if I would like to transform from S, V, and N to P, V, and N, by using a Legendre transform, I cannot. Why? Because P and V are conjugated variables. They are related to each other. P is the derivative of E with respect to V. And I cannot change S by a conjugated variable of V. Okay? This cannot happen. Okay? The three different functions that we have obtained are those. So first of all, this guy, the transformation here, A is E minus Ts. The name is Helmholtz free energy. Okay. If we would like to compute the differential of A, dA equals minus S dt minus P dV plus mu dN. The transformation from SVN to SPN, okay, it is enthalpy, right? SPN, it is enthalpy, H equals E minus PV, okay? This is enthalpy. Okay, the differential of enthalpy, dH, is TdS plus VdP plus mu dN. Okay? Another function of state, so we have already the energy, Helmholtz free energy, enthalpy. The final one that we use is Gibbs free energy. Okay? Gibbs free energy is G E minus Ts minus PV. Okay? Gibbs free energy. dG will be of the form minus S dt plus V dP plus mu dn. We also have other series of transformations that we will, for example, you've seen here that we have kept n exactly the same in all the transformations. We changed entropy and temperature. We changed volume and pressure. We usually will keep n constant. Okay, but we also can invent other functions, okay, and give them our names. The question is, are they important? Those guys are, we will see this in the following, but we can also have other functions as well. Okay, so remember, for energy, we had a variational principle. What our variational principle for energy stated? That in equilibrium, the energy is its minima. Okay? So any fluctuations or imposing an internal constraint, okay, will only give rise to a higher energy. Okay? Delta E under any fluctuation only grows. Okay? For entropy, it was the other way around. For entropy, the entropy was at maxima. So any fluctuations or any internal constraints while keeping energy constant, we're giving what? Giving smaller entropy. Okay? Now, if we will repeat all our considerations, we will take the system, we will impose a constraint, we will let it relax, okay? And we will see what happens to the Helmholtz free energy, to the enthalpy and Gibbs free energy. We will see that there are also variational principles for all those three guys. Specifically, delta A is larger than 0. Delta H is also larger than 0. And the same holds for delta G. Okay. There are variational principles similar to the variational principle of the energy, that all those, they are also called potentials, okay, because they are in some sense similar to energy. Okay, only different variables. So for all those potentials, there are minimal principles. In equilibrium, they are in their minima. Any fluctuation, any internal constraint, we see that they are exactly the same, will give rise to higher Helmholtz free energy, to higher enthalpy, and to higher Gibbs free energy. Now, something that one must remember when looking on all those functions or looking on all this thermodynamic stuff of the 19th century, one must always remember that the point of view, at least my point of view on this stuff, is you're treating system in the same way as you're treating a homogeneous or a continuous function. Okay? The system can be shaped a little bit, it can be pressured, it can be heated up. You perform some small perturbations upon it, and it continuously changes from one state to another. Okay? So all the description of the properties of the system is the same description of continuous functions. Okay? The theory, mathematical theory of analytical continuous functions is the theory of thermodynamics, unless I have some abrupt changes, because when you study functions, functional theory, okay, they're usually continuous, and they have derivatives of the first order, the second order, etc., till we meet functions that somehow they're not continuous. There are abrupt changes. The derivatives do not exist. The same will happen over here. Okay? The equilibrium states or change or some continuous change from one equilibrium state to another is described by a continuum flow and continuum behavior of the potentials, of the energy, of all of this three stuff. Okay? But we will discover that as for functions, there are sometimes abrupt changes. Okay? They become discontinuous, they have jumps, okay? They do not have derivatives or second derivatives. We will see what it leads to for these functions. Okay? Now, before we're going to this interesting stuff, which is called phase transitions, let us derive some properties for equilibrium states that is basically properties of the continuous functions when we assume that E is continuum or A is continuum or H is continuum, what we can obtain from this continuity assumption. So the first thing is Maximal Relations. This is the same Maxwell from electrodynamics. Okay. Relations. Okay. So if I have a function of x and y, okay, and I can write a derivative of this or differential of this function in the following way. I have a dx plus b dy. If this function is continuous, it has the first derivative, it has the second derivative, the following holds. dA to dy equals dB to dx. Okay, this is basically the second derivatives, because what is A? A is df to dx, and B is df to dy. Okay? And it is clear that if the function is differentiable, okay, that d squared f dx dy equals to d squared f of dy dx. We can change the order of the differentiation. Okay. Continuum function, analytical functions, what it gives us. Okay, so we used physics in order to write some properties, like what is the behavior of the energy. Now we use the math of analytical functions in order to discover some relations between the physical quantities. So, an example. We're looking on the Helmholtz free energy. Okay, so Helmholtz free energy, this equation over here. It's dA minus S dt minus P dV plus mu dN. Okay. Now let's assume that we do not have any changes in the number of molecules inside the system. So we're getting rid of this part. Okay. According to this theorem, we are assuming that Helmholtz free energy is a continuous function. So we can use this theorem over here and basically say the following, that ds dv, while keeping what constant? T, equals to dp to dt. Okay, while keeping what constant? V. We don't know what's entropy. We don't know how to measure it. But according to the Maximal Relations, singular still, okay, we know how entropy is changing with volume. Okay? If you want to measure the changes of the entropy with volume, you have to change it to measure the changes of the pressure with temperature. That's it. Let's see another example. Heat capacity, okay, how they are measured or related. So the heat capacity, CV, is T ds to dt, okay, while keeping V constant. What is the derivative of the heat capacity with respect to the volume while keeping temperature constant? It is simply T, okay, d to dV of ds to dt. Okay? So dV here is with respect when the temperature is constant. ds to dt is when the volume is constant. Okay. we can change the order of the differentiation over here, okay? Basically saying it is equals to t dt of d dv of s, t and v. But now ds to dv, according to what we obtained from the first Maxwell relation, is dp to dt. Okay? So it equals to t d squared to dt squared of p, okay? While keeping the volume constant. Okay? Right, so there are plethora of Maxwell relations. What they are based on, let's take a function, energy, enthalpy, Gibbs free energy, whatever you like, okay? Let's assume continuity. Let's assume that the functions are differentiable at least twice, right? And play with it a little bit. Sometimes we obtain something that is actually valuable for the experimentalist of the 19th and 20th century. Sometimes it's another example. Questions? No? Great. For example, okay, by playing the same game, we can obtain that Cp minus Cv is equals minus t dp to dt, t, and dv to dt, p squared. How one obtains this relation? One simply starts with the description of what is Cp. Okay, what is Cp? Cp is T dou S dou T, keeping pressure constant. Okay, and remembering that ds, okay, it is ds dt t plus ds dv, sorry, dv. Okay. A lot of small games that eventually leads to some relations that are actually valuable. But to tell you the truth, that this is basically usually very, very boring, because we are still dealing with continuum functions, differentiable functions. Nothing really interesting happens. Well, maybe with, your nice mathematical theorems on the way. We'll use them at least. Okay. We can play with the properties of the different functions, okay, by using the physical meaning that we put inside them, or physical properties. For example, the energy, this is our initial statement, the energy is an extensive quantity. Okay? This was our opening statement, I think, at the first lecture. It's related to the first law of thermodynamics, right? So what can we dig out from the property of differentiability of energy, okay, and this extensivity, okay? What we can get out of it? Yep.
Sorry, a question. On the previous section, isn't the phrase here should be equal to the derivative of Cv, not the Cv itself?
Oh, yep. You're right. So we started from this. You are absolutely right. Thank you. dCv to dV. Thanks. Okay, so what does extensivity mean? Any other questions? Don't be shy. Yeah.
About that area,
So I assume that S is a function of t and v. I'm playing a game, so I haven't shown you how I got from here to this equation, okay? I'm only telling you that I can start with this definition and play with the properties of the entropy in order to get this one. Okay? I can show you later how. Okay? But it's in the same spirit as the games that I played over here. It depends. It depends. What do you mean? Ah, you mean here. Yeah, this is important. This is important. This is indeed an important quantity. It's dp. This is my mistake. So dp dv. Okay, dp dv and dv dt p. And this is important that here I take p constant and here I have p constant. Thank you. Other questions? Yep.
Yeah. I've been wondering why you calculated the derivative of CP.
All right. So the question is, what is a measurable quantity? Okay.
Why you did it?
Why I did it? First of all, to show you that I can. This is the first answer. The second is, those experimenters sometimes use those relations. So sometimes they cannot compute, okay? They cannot compute, for example, the heat capacity on its own. They can compute the changes in the heat capacity or the changes in the entropy, okay? They cannot control entropy, but they can control pressure and temperature. They have problems with controlling the heat capacity, but they have absolutely no problems with measuring the pressure of the system and changing the temperature. That's it. Okay, so for the sake of those experimentalists, we have all those relations. Other questions? Okay, so we're continuing. So back to the statement. Energy is an extensive quantity and energy is differentiable. Okay? Now what I mean by extensive quantity. So if we have S, and here we have P, for example, okay? Okay. So D, we know that is S dt minus P dv, okay? And we actually can have mu over here. Okay. No, I'm sorry. It is V and N. My fault. My fault. TdS minus PdV plus mu dN. Okay. Now, what I'm saying is extensivity means that the energy is proportional to the size of the system. So the energy is extensive and the entropy is extensive. The volume is also extensive and the number of molecules is also extensive. So what happens if I'm performing the following changes? V goes to lambda V. S goes to lambda S. Lambda is some positive quantity. Okay? And N goes to lambda N. The same lambda. The same lambda. Absolutely the same lambda. Okay? I'm increasing one dimension, for example, of the system by a scale of lambda. Okay? The moment I have done it, okay, this E prime, okay, is a function of lambda S, lambda N, okay, I'm sorry, lambda V, and lambda N. So dE prime equals to T lambda ds, right, minus P lambda dV plus mu lambda dN. Okay. So dE prime, you can take this lambda out of here, equals lambda multiplied by TdS minus p dv plus mu dn, okay? And we have that dE prime equals lambda dE. That means what? That E prime, that is a function of lambda s, lambda v, lambda n, it is simply lambda multiplied by E of s, v, and n. Okay? This is the property of extensivity. Okay? I increase the size of my system, and a proportional increase appears for the extensive quantity. All right? Energy is extensive. I increase the system by lambda. The energy increases by lambda. Entropy is extensive. I increase the system by lambda. The entropy increases by lambda. Okay? But this has a name. This has a name, or let's say a specific property. What is the property of the function that follows this rule? Okay, you have learned it probably, or at least the ones who learn in the math department. It is a homogeneous function. So any function lambda or g, any g of x that satisfies g of lambda x equals to lambda g of x is termed a homogeneous function of the first order. There are homogeneous functions of the second order, the third order, whatever. The order is the power of lambda that I have in this equation. Why it's important? Well, because mathematicians explore these functions in various situations. Specifically, there was a guy named Leonhard Euler that proved a theorem. What was the theorem of Leonhard Euler? First of all, it can be a vector over here. It's not simply a function of one variable. It can be a function of many variables. So the theorem for homogeneous functions is as follows. G of x1 till xn equals to a sum from I goes to 1, from 1 till n, of dg dxi, keeping all the xj constant, multiplied by xi. Any functions that satisfies this relation must be of this form over here. I can prove it to you, but it will take me something like 20 minutes, 30 minutes. And the proof is not really important. It does not teach you anything new. Okay. So if we took this property, so what we know energy is extensive quantity. Specifically, it satisfies this relation, meaning that it's a homogeneous function. And when it's a homogeneous function, it satisfies this theorem by Euler. This means that E is simply Ts, right? So if we have E a function of S, V, and N, okay? So E equals d to ds multiplied by s, keeping v and n constant, plus d by dv, keeping s and n constant, multiplied by v, plus de by dn, right? keeping what constant? Keeping S and V constant, and here I have N. d by ds is t. dE by dV is minus p. d by dN is mu. Okay, so what we have obtained that E is Ts minus PV plus mu n. Okay. Yeah. What function is a homogeneous function? Extensive function is a it's safe to say that extensive function is a homogeneous function of the first order. Okay? More than safe. Okay, so I can hear you. All right, so we have an expression, a new expression for the energy. Now it's like a new tool. You have something, let's compute something else. What else we can compute? Another equation that might be valuable afterwards. So what we know, first of all, we know that E satisfies this equation over here. Okay? On the other way around, what we know that dE is dds minus p dv plus mu dn. Okay? This is our starting point. But let's take the differential of this guy over here and compare it to this equation on the right hand side. So what is dE? Is the differential of Ts minus Pv plus mu n. So what we have here? We have dt multiplied by s plus s multiplied by dt minus p dv minus v dp plus mu dn plus n d mu, and all of this must equal to t ds minus p dv plus mu dn. What we get in the end? Another property that it's related to the continuity, differentiability, whatever you name it, of this equation. So what is actually dying? So that's one, it's TDS, right? dt multiplied by s, tds, right? So what is disappearing? This guy kills this guy, okay? Minus pdv plus mu dn plus mu dn. So we have s dt minus v dp plus n d mu equals 0. This equation have a name. Gibbs-Duhem equation. Okay? And this equation is actually important. We're going to use it. By the same line of reasoning, we can go to the Gibbs free energy. Okay? Gibbs free energy, it's also going to be it's also an extensive function. It's also homogeneous functions of the first order. We use exactly the same properties that we've used for the energy, okay? And we will obtain that Gibbs is, well, first of all, this is a definition, E minus Ts plus PV, okay? Substituting inside of E this guy over here, so it is Ts minus Pv plus mu n minus Ts plus Pv. Okay, what we obtain that G equals mu multiplied by n. And here we have a nice relation for the chemical potential. Mu is G divided by n. Okay. We take the Gibbs free energy, okay, we divide it by the number of moles of the molecules, the number of molecules that we have inside the system, and this gives us the chemical potential. Okay? This is why it's named potential. Gibbs free energy is a transformation of regular energy. And we see that the chemical potential is basically related to this transformation. Okay, so,
Question.
yep.
One of them, G or mu, are measurable?
Okay, energy is measurable.
G is energy?
G is energy, yes. It's like energy, it's like energy. Look, what we have here, energy minus Ts plus PV. What is measurable over here? P is measurable, V is measurable, T is measurable. Not so much, right? And energy. Energy is measurable. You can measure changes in energy, but energy on its own? Not really. But you're using energy in potentials. What you can do, you can take derivatives of the energy and say, those are my forces. And forces are measurable. The same goes over here. You can take the derivatives of the Gibbs free energy. Those would be your effective forces, and you can measure them. So not mu itself, but the derivatives of mu are measurable, right? Okay, so this was something up till now, usual thermodynamics, okay? Described in a little bit of a modern flavor. What we are going to do now, we're going to turn, after we obtain all those nice equations, but they are nice, but they are very simple. Why? Because you need only to assume, well, Stas here is describing properties of continuous functions, and he have used 3 physical quantities, properties, I'm sorry. Okay, conservation of energy, existence of entropy, okay, as an extensivity or intensivity of different quantities. That's it. Everything else that we have done so far is basically deriving some continuum, taking derivatives, taking second derivatives, assuming that the system is going from one place in a continuous fashion to another place, assuming that in equilibrium nothing changes. Properties of analytical functions. What we are going to do now, we're going to talk a little bit more about something that is much more physical. And this is already stability. Okay, so what I mean by stability of equilibrium, stability of equilibrium state. What we know so far, we know properties of different equilibrium states. We know how energy in one equilibrium state is related, okay, to the energy of another equilibrium state. We know that after a while, if the system is left alone, it will reach equilibrium. This is our physical assumption. The question is, what are the properties that determine the stability of the state? Okay, so I reached equilibrium, but if I perturb it a little bit more, will it run away to some different state, or it will return backwards? For any normal, proper physical system, I need the system to be stable. Otherwise, very small perturbations, and there are always small perturbations in the real world, will drive my system out of this equilibrium state. Okay? So the assumption is that any equilibrium state has to be stable. Otherwise, it's not really an equilibrium state, because small fluctuations, small perturbations will lead the system out of the state. Okay? Now, the stability, how I assume or how I choose to describe to you the stability, by performing some sort of a division on a given system. Okay? So let's assume that I have system A, and this system continues to this part. This is system B. I can say that those are two systems. One is A, the other is B. They can be 2 halves, or 1/3 and 2/3 of the same system. The only thing that it's of my interest is that I want to see that those two systems sit in equilibrium with each other. This can be half of system of a global system, or two different systems that are coupled. Okay? And I want to inspect the properties that keep this system, okay, together. What I mean by keep the system in equilibrium, I don't want the system A to grow, and I don't want the system B to grow. Okay? I don't want to see flows, macroscopical flows of energy from system A to system B, or vice versa. I don't want to see flow of matter from system A to system B. Okay? I want to observe the system in a stable state when A is not changing as a function of time and B is not changing as a function of time. There might be some small fluctuations, okay, between those systems, but I want the macroscopical state of A to be constant and the macroscopical state of B to be constant. What are the conditions for this to happen? So first of all, I'm assuming that the energy, okay, that the energy of these two systems is the energy of A plus the energy of B. Now this already is a strong assumption. Why it's a strong assumption? Because there's this borderline over here. Okay. Now I can say that there is an energy EA, I can say that there is an energy EB, but there are also some interaction energy between the two systems. I shouldn't neglect them. Okay? Those interactions might be important. Okay? But still what I'm doing, as I'm claiming that system A and system B are macroscopical systems, basically saying that here is around 10 to the power 23 number of particles, and also here there is around of 10 to the power 23 number of particles. Okay? Under such circumstances, I can assume that the interaction energy is negligible. Okay? When I have only two particles, I cannot neglect the energy of interaction between those two particles. Right? If I have particle A and particle B, the total energy is energy of A plus energy of B plus the interaction energy between A and B. Okay? But if I have huge number of particles, and I'm already not asking what is the energy of particle A and energy of particle B, okay? But I'm asking what is the energy of this huge system and this huge system together, I can neglect those small interactions as long as they are limited in distance. Okay? But for us, we're only assuming that the systems interact with each other only on this borderline. Okay? Why can I neglect the interaction energy? The argument is a scaling argument. I'm saying the following. How many particles are here on the border? Okay? If I'm assuming, okay, that the number of particles, this is a cube, okay, and this is a cube. Okay. So the total number of particles is proportional to the volume of the system and goes as r to the third. Now, if we're looking on the borderline between the two systems, if our systems are three-dimensional, the number of particles that are sitting, okay, in between those systems, it's already not r to the third, or basically before that, sorry. From this, we can obtain that r is proportional to n to 1/3. Okay. The number of particles that are on the border between the two systems are the number of particles that is proportional not to the r, but r2 squared. Okay? Number of interaction particles proportional to r to the squared. Okay? So basically, it's proportional to the n, the total number of particles in the system, the power of 2/3. Okay? So total energy proportional to n. Interaction energy proportional to n to 2/3. Okay. Why? Simply because of the fact that I have small numbers of particles. The dimensionality of the border is r to the second power. That's it. So I have much less particles on the border that are interacting with each other. This interaction might be extremely strong, but they are limited to this border line. Okay? So if I divide the interaction energy by the total energy, okay, energy of interaction divided by E total, it is n to the 2/3 divided to n, okay, which is n to the minus 1/3. The ratio between the interaction energy and an internal energy of the system is proportional to n to the negative power. So when n is extremely big, 10 to the power of 23, the interaction energy is extremely small as compared to the macroscopical system. So for macroscopical systems, unless their interaction is not local and it's not limited to the boundary, okay, I can completely neglect those interactions. They are not important for me. So when I'm looking on two systems, okay, I'm assuming that the total energy is always a sum of system A and a system B. Okay? But this argument holds only if the system is macroscopical. If the system is composed of a very small number of particles, that does not work. But thermodynamics is about macroscopical systems. Okay, so we have our two systems over here. Okay. System A and system B. Okay. And what I'm assuming that I want to obtain some criteria of stability. I'm assuming that the energy of the system, of the two of those systems, is simply a sum of two internal energies. Okay? And in the same fashion as I obtained those variational principles, I want to obtain something that I call stability criteria. Okay? I'm going to say, well, I'm imposing some fluctuation or I'm imposing internal constraints. I know what will happen to the energy of the system. Okay? And by studying those variations, I will obtain conditions about if the system is stable or if the state is stable or not. Okay? So what I'm doing exactly? I'm saying that the total volume of the two systems is a sum of two volumes. The total entropy of those two systems is a sum of two entropies. The total energy of those two systems is a sum of energies. Okay? So when I'm looking on a small change in global energy that occurs, okay, I know that is a change in TA, a small change in an entropy of A, minus P of A, small change in in the volume of A plus a chemical potential of A plus a small change in the number of constituents in the system A. Okay? Plus the temperature of B, a change in the entropy of B, minus P of B, a change in the volume of B, plus the chemical potential of B, a small change in the number of molecules in B. Right? Where I'm going from here? Now let's assume that the total volume has not changed, that the total energy can change, but the total entropy is kept constant, the total volume kept constant, and the total number of particles is kept constant. So what I know that dSA equals minus dSB, dVA equals minus dVB, and dNA equals minus dNB. Everything is kept constant. I'm implying internal constraint. The energy can change somehow, but everything else is kept constant. Okay. Now, if everything is kept constant, and the only thing that I have done is to imply an internal constraint, what must be the change in the energy? Positive. Remember? It is the variational principle for the energy. All that I can do to the system that it's in equilibrium, okay, by imposing constraint or by looking on fluctuations, the only thing that can happen is to increase the energy. The energy is always at its minima. Okay? So this guy is greater than 0. Okay? The moment I have it, okay, okay, I'm looking on the following, that I have something that is greater than 0, okay, and I have here TA minus TB minus PA minus P multiplied by delta SA plus PA minus PB multiplied by delta VA plus mu A minus mu B multiplied by delta NA. Here is a minus sign over here. Okay. This is always positive. When this can happen, delta SA is arbitrary, delta VA is arbitrary, delta NA is also arbitrary. Okay? I impose something, but I can control those small changes. I can make delta A positive, delta SA negative. The same goes for the volume changes. The same goes for the mass changes, but it still have to be greater or equal to 0. The only situation when this equation is satisfied is only when TA equals to TB, PA equals to PB, and mu A equals to mu B. So if two systems are in equilibrium with each other, there are no macroscopical flows, only some small fluctuations imposed by constraints mainly. Okay? The temperatures of those two systems must be the same. The same goes to the pressures, and the same go to the chemical potentials. So if I want to keep two systems in equilibrium, and I don't want that one system will grow in size, okay, or will have additional energy, or will have additional mass as a function of time, those quantities must be satisfied. Okay? Now, by what I mean by saying macroscopical flows, okay? So constant T between the two systems means what? We already have seen it, that there is no flow, okay, no flow of heat. So gradient in T, flow gradient. Flow of heat. Gradient in P, what imposes gradient in pressures? Flow of what? Volume, right? If the pressure in this system, okay, is higher, this system will grow in volume. Flow of volume. If I have gradient in mu, okay, in chemical potential, what will flow from one place to another? The molecules, flow of mass. Okay. So what we see that gradients in temperature, gradients in pressure, gradient in chemical potentials, they impose flow of extensive quantities. Heat is an extensive quantity. Volume is an extensive quantity. Mass is an extensive quantity. Okay? This is why sometimes temperature, pressure, mu, or any given intensive quantity, okay, not extensive but intensive, that is independent of the size of the system, they're called thermodynamical potential, right? Like in physical potential, like in energetic potential, the gradient of a potential imposes flow in the direction of the gradient. The same happens over here. But this is, it's still not stability. Why it's not stability? The only thing that I've used over here, I've used that this is a maxima, or I've inspected a linear change around a maxima. And what I've obtained that this linear change always must be what? 0, right? This equation satisfied only when TA equals TB, PA equals PB, mu A equals mu B. Basically, it's not greater than 0. It's exactly 0. Okay? So this is the first derivative. I've taken the energy. I've said, well, I will change it a little bit. I'm claiming that it's maxima, but I'm changing it a little bit. And this change gives me basically nothing. It's like the first derivative. So the first derivative produces those conditions for equilibrium. But it's still not saying to me if it's a maxima or a minima. I must inspect the second derivative in order to see what are these conditions for stability. Because only minima is stable. Maxima is not stable. What I mean by minima is stable, maxima is not stable. Minima and maxima of a function. Right? If I have a potential energy, the kind of that you learn in the first year. So if I have u of x, okay, and u of x is something like this. So this is a stable point. Okay, if I put a ball, this is my potential energy, and if my ball is basically in this position, if I change it a little bit, if I push it a little bit, it will come backwards and will start to oscillate around this minima. The same will happen over here, right? Stable fixed point. But if I put my ball on the top of this maxima over here, okay, it's not stable. It will run away. If I push it a little bit, it will run either to this side or to that side, and it won't come back if it loses a little bit of energy on its way. So the same goes for my equilibrium. What I've now inspected is that I'll change my system a little bit, nothing happens. Absolutely nothing happens. This equals 0. In order to be sure that I'm at a maxima, or I'm saying to you, I'm in the maxima, I have to actually obtain additional quantities, additional relations that are describing to me that I'm indeed in a maxima. Okay? And I can use this kind of information. Okay. So again, what we are doing, we're going to our two systems, system A and system B, and instead of looking at what is a linear change in the energy, I'm going to look on what is the second order change in the energy. So this is my system A, my system B, okay? I know that no matter what I do, okay, the total energy, the total entropy is going to be the same, the total volume is going to be the same, and the total number of particles is going to be the same. Now, I am imposing local perturbations, okay, such that I'm changing entropy, but I'm not changing the volumes of the two systems, and I'm not changing the number of particles in the systems. Okay? So what I'm claiming is that delta S A plus delta S B equals 0, but delta V A equals delta V B equals 0. So there is no change in local volumes, and the same goes by delta N A that equals delta N B equals 0. What is the second order change in the energy? Okay. It is the second order change in the energy, or second order variation in the energy of A plus the second order variation in the energy of B. By meaning second order, it's simply a second order Taylor expansion. Okay. It is 1/2. What is delta squared A? Is delta EA, okay, delta EA plus 1/2 DEA, D squared EA, delta S A squared, delta S A squared, plus delta E B plus 1/2 delta E B squared by delta S B squared multiplied by delta S B squared. Now, delta EA plus delta EB are around a maxima. They are delta EA plus delta EB equals delta E, and we know that it equals 0 from this equation up here. Delta E to delta S squared squared, okay, it is d to ds of d to ds, okay. D to ds is t, so we have dt to ds while keeping v and n constant. Now dt to ds related to the heat capacity. It's simply T divided by CV. Okay. Now look, what we have over here, this guy and this guy disappears. 1/2 and 1/2 we don't care. Delta SA squared, here we have delta SB squared. But delta SA equals minus to delta SB. So it's the same prefactor. The only difference is this one and that one, okay? But both of them equals to what? To the temperature of A divided by the specific heat of system A plus the temperature of B divided by the specific heat of B. Let's write it down. So delta squared of E equals to 1/2 delta SA squared, okay? Inside here we have T of A divided by CV of A plus T of B divided by CV of B. Now, we are at the minima, right? We want to obtain conditions for stability. This means that this guy is also positive. If this guy is also positive, something what we have to state about these quantities inside. Now, TA, we already know that EA equals to TB. Okay? So what we have, this guy is positive, this guy is a squared of something, so it's positive. So we have 1 over CVA plus 1 over CVB, always positive. Okay. Where I'm going, I want to state something about the heat capacity. I want to state that the heat capacity of any system has to be positive. This is my stability criteria. How I obtain this, that any heat capacity must be positive? Well, I'm saying the following thing. Remember that C in general is dq divided by dt. Q, or dq, or Q is in general extensive property divided by the temperature. Okay? So 1 over CV is 1 over an extensive property. Extensive quantity. Okay? Now, when I took the system, system A and system B, this condition must be always satisfied. I can make one system extremely large and the other system much smaller than the first system. Okay? Since CV is extensive, 1 over CV is 1 over the size of the system. Okay? So the smaller system, okay, the contribution to this sum, it's disproportional to the size of the system. The smaller the system is, the stronger, okay, its part in this equality over here. So since the separation between the two systems is arbitrary, okay, I can always say, well, I have taken one big system, another one small system. The big system is not going to contribute much because it's 1 over the size of the system. And it's only the smaller system that it matters, okay? And it's always positive. Then I obtain that CV is larger than 0. Okay? Always. Why it's important? Why it's important for me that the heat capacity must be larger than 0? Consider the following situation. I have two systems. There are a difference of temperatures between them. We couple them together, okay? We couple both of those systems together. Because of the differences in the temperature, there is going to be a flow from system A with a higher temperature to a system B with a lower temperature. CV is how the heat of the system is changing with the temperature. Or the other way around. 1 over CV is how the temperature of the system is changing with the heat of the system. So if there are a flux of heat to the system, and if we will assume that the heat capacity is negative, what is going to happen? I am adding up heat to the system. Because I add up heat to the system and the heat capacity is negative, the temperature of the system is going to go down. Okay? So by adding heat to the system, I'm cooling it down. I'm cooling the system down. There is a higher gradient between the two systems, and there's going to be more heat flowing from the hotter system to the colder system. Okay? Basically, it will push me outside of equilibrium. There is no stable point. The only stable point is that as I add heat, the temperature is growing. That's it. Okay? And this is described by the heat capacity. If it was the other way around, as I add up heat, I am cooling down the system. Okay? I'm cooling down the system, I'm enlarging the gradients, I'm enlarging the gradients, I'm adding more heat, I'm cooling more, etc., etc., etc. Okay? So this is not a stable physical situation. Then what we must have that the heat capacity must be larger than 0. We can do the same thing, but not for the energy, but for enthalpy. Okay? You can repeat all those dances with equations and obtain that also Cp is greater than 0. Okay? Again, the same variational principle. You are assuming that you are in a minima, you expand around this minima, okay? And you obtain a quantity that defines the stability criteria of your potential. It can be a minima of an energy, it can be a minima of an enthalpy, Gibbs free energy, whatever. Okay? But the point is, since it's a minima, there are some conditions that must be satisfied, and those are the conditions. So equilibrium means that there is equivalence of temperatures, pressures, chemical potentials. Stability means that the heat capacities are positive. Because the other way around, there would be heat flowing from hotter system to cooler system, and the cooler system would be even more cooler, etc., etc., etc. Okay. We have 10 minutes left. I don't know why, but 10 minutes. And in those 10 minutes, I would like to start a discussion about phase transitions. 10 minutes. Okay. Now, so far, what we've gained some sort of understanding of is that we look on the system as a continuous function, we look on a state, and a state can change in a very continuous fashion. The stability of two systems dictates that there is some equivalence, okay? But sometimes the equivalence of different quantities does not mean that they are not changing abruptly. Okay? So what I'm trying to say to you is that if you're looking on two systems, or part A of the big system and part B of the same system, okay, what we know is that mu A equals to mu B, right? T of A equals to T of B, the same temperature, and P of A equals to P of B. Now, of all those different equations that we derived previously, the one that's important is the Gibbs-Duhem equation. The Gibbs-Duhem equation states the following, that S dt minus V dP plus n d mu, okay, equals 0. Or I can rewrite it as d mu equals to S divided by n minus S divided by n dt, okay, minus V divided by n, or plus dP. Okay. So mu, okay, at least from the Gibbs-Duhem equation, I can write always mu as a function of the temperature and the pressure. Mu is a function of temperature and pressure. Okay? So let's look on the two systems of ours, and we're saying that the temperatures of those two systems are equal to each other. The pressures of those two systems are also equal to each other. All right? This means that, well, if they are in equilibrium, that the chemical potential of system A is also equal to chemical potential of system B. Now, the equation over here states the following. So if everything is in equilibrium, all right, I'm changing the temperature, okay, I'm changing the temperature. The chemical potential of system A is going to change slowly. The chemical potential of system B is going to change slowly. And in order for them to be in equilibrium, okay, they must be exactly the same. Okay. But, and this is an important quantity, if mu is a continuous function, okay, an analytical function, nothing really happens. I change a little bit more the temperature, okay, of the system A and system B. The pressure, I change it also a little bit more, and the chemical potential also changes a little bit. Nothing happens. But in some situations, mu can have jumps, right? Or mu can be discontinuous, or the derivatives of mu can be discontinuous. Okay? So I can have equivalence of the chemical potentials between the two systems, but how the chemical potential of system A changes when I increase the temperature is different from the way of how the chemical potential of system B changes when I increase the temperature. Because there are some differences, not in the chemical potential itself. So the chemical potentials can be exactly the same. So the systems can be in total equilibrium with each other. But the gradients of the chemical potentials can be different. The derivatives of the chemical potentials can be different. And this means that the two systems are going to be in equilibrium with each other, but they are going to be somehow really, really different from one each other. Okay? Let's look on this graphically. So we have here T. We have here P, and we have here the axis of mu. So let's assume that this plane here is a hyperplane, which is the function, which is mu of T and P of system A. Okay? This is how the chemical potential of system A behaves, okay, as a function of the temperature and the pressure. We know that the chemical potential must be a function of temperature and pressure. We can look on system B and say, well, they are somehow, no, this is a one. They are in equilibrium with each other, right? But the behavior of mu for system B is different. It goes something like this. Right? So it's a different behavior. The behavior of mu for system B is different than the behavior of mu for system A. We can say, well, but they are in equilibrium. Yes, they can be in equilibrium if you're looking on a set of parameters that actually sets mu on this line over here. Okay? What will happen to the chemical potential if I'm going from one temperature to another along this line, or crossing this line? Okay, so let's now look at this hypersurface over here is a total chemical potential. The behavior over here basically says that if I'm crossing this line, okay, mu is almost not changing from this point to that point. Nothing really happens, right? Mu is a continuous function. Okay? Nothing really happens. But what happens is that the derivatives of mu are discontinuous, right? So I'm changing the temperature a little bit, okay? The system is stable, nothing really happens, okay? I'm going from this point on my hypersurface to that point on my hypersurface, okay? Mu is continuous. But the derivatives of mu, if I'm performing this change, the derivatives of mu are going to jump. Okay, so mu describes my system, and I found a region over here when d mu to dt is discontinuous, or d mu to dp is discontinuous. It can happen. Nobody assured me that everything should be continuous and differentiable all the way around. I can have such a behavior of the chemical potential. Now, why it's important? So I have a discontinuous derivatives of this chemical potential that I even cannot really feel what it is. Well, does it mean that I have a discontinuous behavior of the derivatives of mu? d mu to dt, according to this equation over here, okay, d mu to dt equals to minus s divided by n. d mu to dp equals to v divided by n. Okay, so discontinuous d mu to dt means discontinuous s divided by n. When I'm going from this point, okay, I'm having a specific temperature, a specific pressure. Let's keep the pressure constant and change the temperature a little bit. Going from this point, that's the chemical potential is A, to this point that the chemical potential is B. The system is stable. Okay, I've made a very small change. There was a jump in the derivative of mu. A jump in the derivative of mu means a jump in the entropy. The entropy is jumping. Okay, I can say, well, no, let's keep temperature constant, but change P a little bit. Change P a little bit. The derivative of mu with respect to P is discontinuous. The volume behaves in a discontinuous fashion. The volume of the system jumps. So are you familiar with the phenomena where I change the pressure or I change the temperature and the volume of the system changes abruptly? Not slowly, but abruptly. For example, I'm heating water. I'm heating it and I'm keeping the water around 60 Celsius. Nothing happens. 70 Celsius, nothing happens. Around 100 Celsius, I will start to see bubbles. What are those bubbles? It is water. It was the same material. I have added nothing inside. And suddenly I see bubbles inside my kettle. Where they have came from? Okay? They came from a phenomena that I am terming a phase transition. Okay? My chemical potential of the system changes slowly from one point to another. Okay? But it changed in such a fashion that there was a jump in volume. The jump in volume means, okay, I had water, bubbles, there are bubbles of air. The volume of air is much bigger than the volume of the liquid. Okay? So this was a transition from one state that I termed liquid to another state that I'm termed gas. Okay? What happens during this transition? I observed a jump in the volume. This means that my chemical potential, according to this reasoning over here, my chemical potential, or more specifically, the derivatives of my chemical potentials, change abruptly. Okay? So all those phenomenal phase transitions, changing from one state of matter to another, from liquid to gas, from gas to solid, okay, from ferromagnetic, okay, to non-magnetic, or different states of matter, we can study them instead of just saying, well, I have gas over here, I have liquid over here, I have ice over here, and I have water over here. Instead of just saying those words, we start to understand that the thing to study is the chemical potential of the system. Okay? And by studying the properties of the chemical potential of the system, we will gain some sort of information when the system changes from one phase to another, and how this change occurs, and can be maybe dictate the system not to change to something else. We'll see about that not tomorrow, but on Tuesday. Thank you.